Historically, our grandest views of deep space came from Hubble. As of July 2022, however, a superior space telescope has emerged. The James Webb Space Telescope takes us beyond what anything else has seen. From planets to nebulae to galaxies nearby, all the way to the distant universe, the James Webb Space Telescope has taken us beyond what anything else has seen about the universe. Although each image taken so far was revolutionary in its own way, the observatory has continued to explore the universe, revealing features that were previously unknown and unseen. And in a recent groundbreaking observation, the Webb has focused its big eyes on the center of our Milky Way galaxy, detecting a bunch of objects that shouldn't exit. Join us as we dig deep into James Webb's mind, blending discovery that could unravel a decade-old mystery about our galaxy. Our modern perspective on the universe is, simultaneously, both a triumph and a tragedy. The triumph is how, from our location around a random star inside a typical galaxy in a vast universe, we've been able to learn so much about the cosmos we inhabit. We've discovered the laws that govern the universe as well as the fundamental particles that make up reality. We've developed a cosmological model that can explain how the universe came to be the way it is, with observations that take us from the present day back to the far reaches of the universe. Over 13 billion years ago and more than 30 billion light years away in space. After countless generations of wondering, we finally know what the universe looks like. But there is tragedy in this story as well. All that remains unknown about the cosmos. We know that the normal matter we see under our currently known laws of physics are insufficient to explain the universe on small and large scales. Both dark matter and dark energy, at minimum, are required. We have an unresolved controversy over how fast the universe is expanding. We've never seen the very first stars or galaxies. We've never measured the atmospheric contents of an Earth-sized exoplanet. We don't know how supermassive black holes first formed, and the list goes on, but now we have our best opportunity to solve them. As the premier space observatory, the James Webb Space Telescope would teach us the answers to all of these questions, and plus more. James Webb comes with significant advantages over any previous mission. First and foremost is its size. Webb features a 6.5-meter mirror composed of 18 gold-plated hexagonal segments. This colossus gathers more than 6 times as much light as the Hubble Space Telescope's 2.4-meter mirror, so it can record light from objects 6 times faster than its predecessor. But Webb's sensitivity to infrared light is the real game changer. The space telescope can view wavelengths from 0.6 to 28.5 micrometers, from the red end of the visible spectrum to the mid-infrared. Hubble's optics are optimized to record radiation from 0.09 micrometer in the ultraviolet to 2.5 micrometers in the near-infrared, with the majority of its sensitivity centered on visible light. Perhaps surprisingly, in its intended infrared domain, the Webb telescope generally won't resolve finer details than Hubble achieves in optical light. Although resolution increases with mirror size, it also diminishes with wavelength. Observing in the infrared allows astronomers to see galaxies that existed less than a billion years after the Big Bang. These distant objects emit ultraviolet and visible light, but the expansion of the universe shifts this radiation to longer infrared wavelengths. Peering into the infrared is the only way to observe these young galaxies from Earth's vicinity. The same holds true for newly forming stars. The dust that envelops infant suns scatters visible light, hiding what lies within from our eyes, but it lets infrared radiation largely pass through. Despite its focus on distant galaxies and star formation, James Webb is an all-purpose observatory. Its powerful infrared eye sees details in Milky Way objects beyond the reach of conventional telescopes. James Webb Telescope adjusted its focus to view Gaussian galactic center of our Milky Way galaxy for week. The rotational and barycentric center of the Milky Way galaxy is known as the galactic center. Sagittarius, a star, A compact radio source that is almost perfectly at the galactic rotational center, is the galaxy's central massive object and is a supermassive black hole, with a mass of roughly 4 million solar masses. The Milky Way's brightest points, the butterfly cluster or the star Shala, are visually close to the galactic center, which is roughly 26,000 light-years from Earth in the direction of the constellations Sagittarius, Ophiuchus, and Scorpius, Ophiuchus, and Scorpius. To the south of Galcin is the Pipe Nebula. Within 1 parsec of the galactic center, there are about 10 million stars, most of which are red giants. There's also a sizable population of enormous supergiants and Wolf-Rayet stars that resulted from star formation in the area about 1 million years ago. Within the considerably larger galactic bulge, the core stars make up a very minor portion. Clouds of obscuring dust and gas shield the center of our Milky Way galaxy from the inquisitive eyes of optical observatories. The infrared cameras on the Spitzer Space Telescope, however, can see through much of the dust in this breathtaking scene and has previously been able to identify the stars in the dense galactic center region. A significantly enhanced infrared vision will be available with the James Webb Space Telescope, giving it the ability to reveal smaller stars and finer features. A 4 million times more massive black hole than our Sun is located in the heart of our galaxy, surrounded by millions of stars moving at breakneck speed. Extreme ultraviolet and X-ray rays flood this hostile environment. However, a large portion of this activity is hidden from our view because it is covered in interstellar dust. The James Webb Space Telescope from NASA is built to observe the universe in infrared light, which is not visible to the human eye, but is crucial for observing celestial objects covered in dust. Infrared light that has pierced the dusty shroud will be collected by Webb after launch, showing the galactic center in unprecedented detail. And in a recent world-shattering observation, the Webb telescope has just spotted there's a stellar fountain of youth birthing new stars near the Milky Way's central black hole, where they shouldn't be able to exist. Near the galaxy's supermassive black hole, strong radiation and gravitational forces create extremely inhospitable conditions for new star formation. However, for decades now, astronomers have seen young stars near the galactic center, defying all their predictions. A particular cluster of young stars known as IRS-13 was discovered over 20 years ago, but had been difficult to assess how old its stellar components are. Using data collected by a wide range of telescopes over many years, however, Piesker and colleagues finally found the stars in IRS-13 to be much younger than expected. The stars in IRS-13 appeared to be around 100,000 years old, which is extremely young in cosmic terms. For instance, our middle-aged star is around 4.6 billion years old, meaning the Sun is 46,000 times older than the stars of IRS-13. As study lead author Florian Piesker, an astronomer at the University of Cologne's Institute of Astrophysics, said in a statement, "The analysis of IRS-13 and the accompanying interpretation of the cluster is the first attempt to unravel a decade-old mystery about the unexpectedly young stars in the galactic center." In addition to IRS-13, there is a star cluster, the so-called S cluster, which is even closer to the black hole, and also consists of young stars. They are also significantly younger than would be possible according to accepted theories. The discovery of such an abundance of youthful stellar bodies at the heart of the Milky Way is shocking because it was previously thought that high-energy radiation and immense tidal forces generated by gravity in this central region would disrupt star formation. That should have prevented young stars from gathering around Sagittarius, a star, and in the vicinity of the galactic center. But this isn't the only shock the heart of the Milky Way has delivered to scientists recently. In a separate study, the James Webb Space Telescope was used to discover water ice at the Milky Way's galactic center. This is connected to the recently found wealth of young stars in the region because water ice is commonly found in disks of dusty material that surround young stars called protoplanetary disks. Water ice also indicates the unexpected youth of stars around Sagittarius, a star. Piesker and his team think that IRS-13 may have experienced a turbulent formation, theorizing that the star cluster was pushed towards Sagittarius, a star. The cause of this migration could be friction generated by interactions with dust and gas that lies between stars, the interstellar medium. Or it could be collisions between IRS-13 and other star clusters. This movement would have resulted in gas and dust piling up at the leading edge of the star cluster, almost like how a working snowplow builds up a wedge of icy material while sweeping the streets. Stars form in overly dense regions of gas and dust, so this compression of material would trigger the birth of new stars in IRS-13. Once IRS-13 was close enough to Sagittarius, a star, the cluster with areas of active star birth would have then been captured by the immense gravity of the supermassive black hole. The team now intends to study IRS-13 further in order to determine the effects supermassive black holes like Sagittarius, a star, can have on their surroundings and regions of galaxies not in their immediate vicinity. As team member and Masaryk University scientist Michael Zajakic explained, the star cluster IRS-13 seems to be the key to unraveling the origin of the dense star population at the center of our galaxy. We have gathered extensive evidence that very young stars within the range of the supermassive black hole may have formed in star clusters such as IRS-13. This is also the first time we have been able to identify star populations of different ages, hot main sequence stars and young emerging stars in the cluster so close to the center of the Milky Way. In another remarkable discovery, NASA's James Webb Space Telescope has detected evidence of something unexpected surrounding a distant Jupiter-like exoplanet, WASP-17b, which researchers involved with the discovery say is the first observation of its kind. 1,300 light-years from Earth within the high-altitude clouds of the exoplanet WASP-17b, researchers say they have found evidence for the presence of quartz nanocrystals, marking the first such observation in a discovery made possible by Webb's Mid-Infrared Instrument, or MIRI. Located within the constellation Scorpius, WASP-17b was discovered in August 2009, one of the largest exoplanets ever discovered. Among the unique properties that distinguish it from its nearby planetary neighbors is the fact that it is also the first planet scientists have discovered that possesses a retrograde orbit, which sees it moving in the opposite direction of its nearby star's rotation. It also has a very short orbital period of slightly less than 4 Earth days, which makes it an ideal target for astronomers employing techniques like transmission spectroscopy, which measures the way starlight is scattered and filtered as it passes through an exoplanet's atmosphere. Although the planet's unusual retrograde orbit had already made it an outlier that upended our previous understanding of planetary formation theory, the new observations made by the Webb telescope are adding to WASP-17b's mystery, since particles of silica have never been previously observed in a distant planet's atmosphere. David Grant with the University of Bristol, UK, who is part of the research team that made the intriguing discovery, said that although they knew that aerosols were likely to be found in WASP-17b's atmosphere based on past observations by Webb's predecessor, the Hubble Space Telescope, Webb's predecessor, the Hubble Space Telescope, didn't expect them to be made of quartz. Grant is the lead author of a new paper detailing his team's findings. Co-author Hannah Wakeford, also from the University of Bristol, agreed that the discovery came as a complete surprise to the team. He said in a statement that we fully expected to see magnesium silicates, but what we're seeing instead are likely the building blocks of those, the tiny seed particles needed to form the larger silicate grains we detect in cooler exoplanets and brown dwarfs. Minerals whose compositions are rich in oxygen and silicon, known as silicates, are extremely prevalent on Earth and the Moon, and are believed to also exist in abundance throughout the galaxy. Although silicates have been previously detected in exoplanet atmospheres, as well as those of brown dwarfs, those discoveries involved silicates composed mainly of olivine, pyroxene, and other magnesium-rich minerals. The discovery of silicates composed of quartz alone in WASP-17b's atmosphere marks yet another unique discovery that builds onto the many intriguing aspects of the exoplanet's composition and behavior. Particularly, The team's discovery provides new insights into the dynamics of how the clouds enveloping exoplanets form and evolve over time. While observing WASP-17b over the course of a 10-hour period, Webb was able to gather more than 1,200 brightness measurements of infrared light emissions as the planet passed in front of its star, providing enough information for each wavelength to be calculated. To the team's surprise, an unusual spike appeared at 8.6 microns, which was very different from what would be expected if the clouds surrounding the exoplanet had been filled with magnesium silicates, as in past observations, pointing to the presence of quartz silicates instead. Each of the quartz nanocrystals is likely to be about a millionth of a centimeter across in length, but possessing prismoid shapes similar to quartz grains as they appear on Earth. But unlike minerals that find their way into clouds on our planet from the Earth itself, the quartz nanoparticles in WASP-17b's atmosphere are believed to have their origins from within its atmosphere, where conditions are right for the formation of solid crystalline forms directly from the hot gases that are abundant. In these conditions, solid crystals can form directly from gas, without going through a liquid phase first, Grant said in a statement. Grant and the team believe that their findings could help astronomers understand not only the composition of clouds in the atmospheres of exoplanets like WASP-17b, but also may reveal underlying processes in the formation and evolution of exoplanets. While the exact composition of these clouds is largely unknown, this information is vital to understanding the chemistry and energy budget of planetary atmospheres. The team writes in their recent paper, "These beautiful silica crystals tell us about the inventory of different materials and how they all come together to shape the environment of this planet," Wakeford said. As breaking new, artificial intelligence, or AI for short, could soon be doing your supernova hunting for you. A new, fully automated machine learning algorithm has successfully detected, identified, and classified its first supernova, the first time this has been achieved with AI. The program, called Bright Transient Survey Bot, could vastly accelerate the process of analyzing and classifying supernovas, its developers say. Spotting supernovas currently depends on humans and computers working in conjunction, but Bright Transient Survey Bot could cut us out of that equation. According to the Bright Transient Survey Bot team, over the past 6 years alone, human astronomers have spent an estimated 2,200 hours visually inspecting and classifying supernova candidates. Bright Transient Survey Bot could allow astronomers to redirect this effort and spend more time investigating the origins of these stellar explosions and modeling how they proceed. As team leader, Adam Miller, a professor of physics at Northwestern University in Illinois, said in a statement, "For the first time ever, a series of robots and AI algorithms have observed, then identified, then communicated with another telescope to finally confirm the discovery of a supernova. This represents an important step forward as further refinement of models will allow the robots to isolate specific subtypes of stellar explosions. Ultimately, removing humans from the loop provides more time for the research team to analyze their observations and develop new hypotheses to explain the origin of the cosmic explosions that we observe," Miller added. Many supernovas occur when dying stars exhaust their fuel for nuclear fusion. Unable to support themselves against the inward push of gravity, these stars' cores collapse while their outer layers blast out as supernovas. In the case of Type 1, supernovas, explosions are triggered when a stellar remnant called a white dwarf exists in a binary system and is stripping matter from its companion star. This influx of material causes white dwarfs to reignite and explode, destroying them entirely. These supernova explosions can be so bright that they outshine the combined light of every star in the galaxy around them. Thanks to the vastness of space, however, even this incredible burst of light doesn't mean supernovas are easy to spot. Currently, robotic telescopes scan the night sky, capturing repeated images of the same patch of space, hoping to find a changing or transient object that wasn't in previous images. Automated software presents a list of candidate explosions to humans, who spend time verifying the candidates and executing spectroscopic observations, Miller said. We can only definitively know that a candidate is truly a supernova by collecting its spectrum, the source's dispersed light, which reveals elements present in the explosion. There are existing robotic telescopes that can collect spectra, but this is also often done by humans operating telescopes, with spectrographs. To potentially remove humanity's role in these proceedings, Miller and his team developed Bright Transient Survey Bot and trained the AI with over 1.4 million historical images from nearly 16,000 sources. These included confirmed supernovas and other explosive astronomical phenomena like the temporary flaring of stars, stars that are periodically variable stars, and the flaring of galaxies. In order to test their new AI tool, the researchers set about hunting for a newly spotted supernova candidate designated SN2023 Tyche, which is believed to be a type Ia supernova located around 760 million light-years from Earth. The supernova was found by the Zwicky Transient Facility, or ZTF robotic telescope for short, on October 3. As it searched ZTF data, Bright Transient Survey Bot was able to identify SN2023 Tyche on October 5, after which it collected the potential supernova spectrum from the robotic telescope at Palomar Observatory, known as the SED machine. Thus, through this automatic collaboration, CN2023 Tyche was classified as a Type 1 supernova. Bright Transient Survey Bot didn't even need its human operators to get the word out, as this information was automatically shared with astronomers by the AI on October 7. As Northwestern graduate student Nabil Rahimtullah, who co-led the Bright Transient Survey Bot technology development with Miller, said in the same statement, "The simulated performance was excellent, but you never really know how that translates to the real world until you actually try it." Once the observations from SED machine and the automated classification came in, we felt a huge wave of relief. The beauty of it is that once everything is turned on and working properly, we don't actually do anything. We go to sleep at night, and in the morning we see that Bright Transient Survey Bot. And these other AIs unwaveringly do their jobs. As a piece of good news, NASA is mobilizing the scientific community to ensure the agency's next big space telescope will be ready to deliver a big-picture view of the universe almost immediately after launching. The Nancy Grace Roman Telescope, also known as the Roman Space Telescope, or just Roman, is set to launch in 2027 and will view the cosmos with a staggeringly wide field of view. Its big picture, observations of distant and early galaxies, could help scientists solve the mysteries of dark matter and dark energy. Collectively, this so-called dark universe accounts for 95% of the energy and matter in the cosmos. Yet the true nature of dark matter and dark energy eludes scientists. The work of the scientific community could help Roman's operators deal with the deluge of data it delivers when it opens its eyes to tackle these mysteries and hunt for planets outside the solar system. By supporting the existing infrastructure calibrating Roman, this effort will maximize the scientific potential of the instrument, which began as the Wide Field Infrared Survey Telescope before being renamed in honor of Nancy Grace Roman, NASA's first chief astronomer. According to Julie Massineri, a senior project scientist for the Roman Space Telescope at NASA's Goddard Space Flight Center in Greenbelt, Maryland, we're harnessing the science community at large to lay a foundation, so when we get to launch, we'll be able to do powerful science right out of the gate. There's a lot of exciting work to do and many different ways for scientists to get involved. Roman's view of the cosmos is so vast that the telescope will collect tremendous amounts of raw data consisting of trillions of individual measurements of stars and galaxies over the course of its 5-year primary mission. Therefore, a fast and efficient way to identify patterns in this data will be crucial. Simulations are currently being performed that will test machine learning algorithms' ability to spot various cosmic phenomena and thus identify these patterns. As Massineri said, the preparatory work is complex, partly because everything Roman will do is quite interconnected. Each observation is going to be used by multiple teams for very different science cases, so we're creating an environment that makes it as easy as possible for scientists to collaborate. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.